works for Google at the cloud team and for the developer relations. And today he's going to talk about deep learning with Python and TensorFlow. So let's give him a big hand.
Thanks a lot. Like he mentioned, I'm going to be talking about deep learning with Python and TensorFlow. This is going to be a fairly introductory talk for folks. So how many of you are actually kind of machine learning folks that do machine learning who've played with TensorFlow or Theano or any other library? How many of you guys do that? Yeah, so a fair number of you. So just to set expectations, this is going to be a fairly introductory talk for things like deep learning and machine learning. But I hope that you get a little bit out of it and kind of get an idea of how TensorFlow works. Like I said, my name is Ian Lewis. I'm a developer advocate on the Google Cloud Platform team. I am based in Tokyo, Japan, so I do a lot of traveling around to APAC to help support developer communities and make it easier, work with developers to make it easier to use Google Cloud Platform. I'm also on Twitter if you guys are interested in Twitter. That's my name is Ian M. Lewis on Twitter. So if you're interested, just give me a follow, and I'd love to hear from you if you have any questions or ideas after the talk as well. So first, I want to give a little background about deep learning and what deep learning is, and why all this is important. So deep learning is a type of machine learning that is specifically, when you're talking about deep learning, you're talking about a specific part of machine learning that is specifically you're talking about something called neural networks. And neural networks, and then specifically you're talking about a type of neural network that is a deep neural network. And deep neural networks are basically a type of, or a neural network is a type of tree structure, and specifically you're talking about this, like these very deep type of tree structures that build up neural networks. And I'll talk a little bit about what that means in the following slides here. So the idea is that basically you'll be able to do things that are, teach a machine to do things that normally humans would be doing. So things like recognizing that this picture is a cat. Obviously, all of you know that this is a cat, but being able to teach a machine how to do that is something entirely different. So a neural network are typically designed in these kind of layers. So what you would do is you give the pixels for this particular cat image into this neural network, and then these layers, or each of those pixels, might represent an input value, which gets inputted to the layers, and each of these, like in this yellow layers, these are called hidden layers inside of a neural network. So the blue is the input layer, and the yellow one is a hidden layer. That's part of the internal part of the neural network, and then you have the output layer, which is the green one. And so each one of these nodes contains basically an activation function. It does something to the data, and then all the inputs are connected to each of the internal hidden nodes, and these are basically connected by a weighted connection. So each of these has a weight. So that bottom input node might have a slightly different weight depending on which node or internal hidden layer node it's connected to. So what types of problems are these neural networks able to solve? So just to give an example, this is the types of things that these neural networks are really good at is being able to do things like classification. That's one major area or major problem that it's able to solve well, as well as regression problems. So this particular example here is a classification problem. So you have two different classes, blue and orange, and you want to be able to tell which one is which. So let's take a look at what that might look like, and kind of talk a little bit more about that, what that might mean. So here's this is a little visualization that you can do on how a neural network works. So say you have a classification problem, like you have, this might be the height or weight of a person, and then this might be the height, and this might be the weight of a person, and then these different classes might be like, say, a child or an adult, and you want to be able to tell that a computer how to classify this. And this is actually a really, really easy classification problem because you can just draw straight lines through this. So in reality, you don't even need a hidden layer. You can just give it these the inputs and outputs, and it will be able to figure out how to classify each of these. But if you want to give it a slightly more difficult problem, like say this, where you have a one class that's in the center of another class, being able to train this is not quite as easy. So you wouldn't be able to train this and tell it to figure out which one's which just by giving it these x and y inputs. So you could add these hidden layers, and each of these layers adds a different kind of aspect to the network. So here these are each doing their own kind of classification. And then each of these are rated based on how well they classify the data here, and then those are then weighted based on how good they are, and then the result is combined to give the final result. So here, say we just have two nodes, we can add up these two classes, or what these two neurons give you, and you can kind of get closer to what you're looking for. So it can give you kind of this two-dimensional, based on two lines. So then you can give it, say, another hidden layer, and then, finally, it's kind of able to build something that looks kind of like a triangle. So here, it's actually combining the different layers here. You can see that it actually combines each of these three kind of lines that it's used to classify, and then combine that into an actual triangle kind of shape here. So it's kind of doing this combining and weighting within the neural network. And that's essentially how it works. But most really useful problems are much more complicated. So something like this would require a quite more complicated neural network. So say something that's a little bit deeper. So in this case, we're adding a couple more hidden layers and a bunch more neurons. And so by adding these new layers, you can actually do something a lot more complicated, or be able to classify a lot more complicated problems, because each of the outputs of these neurons, or this layer, can go to another layer and then create more complicated patterns. So you can see that these are much more complicated types of patterns that you can then combine to a final output. So if you tell this to train, this will take a little bit of a while. Hopefully it would get somewhere. It's actually not. Sometimes it's a little bit difficult in order to pick which, or to find a type of machine, or a type of a neural network that will actually give you the right kind of output. So here, if I train this a little bit longer, hopefully it'll go somewhere. So it's getting closer, but it doesn't look like it's going to actually get there very well. Maybe if I redo this, regenerate the data, and then add. But basically by building these kind of more deep neural networks, you can actually kind of solve much more difficult problems. And that's basically the idea behind these deep neural networks. So I kind of want to jump back to the slides, but so essentially what you're doing within a deep neural network is you're creating this kind of big function that is going to take in a cat or some sort of input, in this case a cat image, and then do these kind of transformations on them. Each one of these is an activation function, And then in between each of the different layers, you're actually passing what's called a tensor. And I'll talk a little bit about what tensors are in a second. But each of these layers can then be used to do things like determine the different features and patterns within the image, like, say, what a cat's eye looks like, or an ear, or a nose, or things like that. And then eventually they get combined to actually figure out that it's a cat in the image. So what is a tensor? So these tensors are the type of data that you're passing around within this function. But I think that you're probably all familiar with things like x and y coordinates, or x and y and x, y, z coordinates, like in 3D. But these are both examples of tensors, but tensors can be quite a bit more complicated. So you can imagine, say, a point somewhere in n-dimensional space as being a tensor. But so one-dimensional space, or three-dimensional space, or two-dimensional space are types of tensors, but tensors can be quite a bit more complicated. And with computers, you actually represent these as arrays. So in a computer program, you might create a vector by using an array, or a matrix by using a three-dimensional array. But a tensor is essentially just an n-dimensional array. It can be any number of dimensions. So that's essentially what a tensor is. It's not like really common language, so I just wanted to go through and talk about that. But then what you can actually do with these tensors is, like, you can build the neural network this way by having the tensor as, or the values in the tensor as the input, and then having each of the weights be applied to a tensor using kind of matrix multiplication, or like tensor multiplication, or multiplication by these weights, and then adding biases. So quite a lot of the ways of building a neural network involve these kind of operations on tensors or on matrices. And then finally, you would build, after you've done several of these operations, you can then apply what's called a softmax to it, which will help normalize the output data. So essentially what you're doing is you're building each of these weights is assigned to a particular value within the tensor, which gives, in the output, a type of evidence for, say, if this type of cat eye is in the image, then probably you're looking at a cat, or that type of thing. And then eventually you apply the softmax to actually normalize it into giving you some kind of percentage that's between, like, say, 0 and 1. So at the end, you get, like, this kind of tensor that says, like, or finally you get a tensor at the end that says, like, it has a bunch of probabilities in it that it's a cat or a dog or something else, or it's ever one of any number of classes. But and you can use the exact same model to actually train, or the exact same thing to actually train the neural network. So here, what you do is you actually use something called backpropagation to train a network. And what you do is you will run the data through the network and then train it, compare the output of the network to the values that it's expected to have. So you would train it on, say, a cat image and a label that says it's a cat, and then compare the output of the network to the fact that it's whether it's a cat or not. And so, say if the first time it comes back and it says, well, it's about 20% that it's a cat, well, it should be much higher than that. And so you'll apply what's called a loss function to that in order to update the weights within the neural network, and thus continue to train it. And so you'll run through this many times over in order to adjust the weights that go back into the neural network. So here, what we're doing is actually this part here is the neural network, and then we train this is the training data, which gets added to the loss function, and then a gradient is applied to that, which then gets which then is used or updated, used to update the weights and biases that are then fed back into the neural network here. And then you continually do that over and over again in order to train the network. So that's a little bit of background about what a network is and how you train it and what it's actually doing kind of under the covers. But why are people even talking about neural networks all of a sudden? There's a lot of people this has become a kind of a big buzzword or something that people are talking a lot about. So why is that? One of the reasons for that is that there's been kind of a number of breakthroughs that have happened in the recently that has allowed deep neural networks to actually become very useful for applications. So I want to explain what that means, though neural networks are pretty simple in principle, like you're basically doing these kind of tensors and matrix kind of multiplication, you typically need to create a fairly complex graph, something like this, in order to do something useful, like tell that an image is a cat, or that it's a dog, or whatever. So this is a visualization of Google's inception model, which is used as part of Google Photos in order to tell that what images are, like cat or dog or a photo or an automobile or whatever. So it's not super hard for somebody to go through here and parse what it's actually doing, but it becomes a fairly long and a deep graph, and each of these is doing kind of matrix multiplication, addition or a number of operations, which each have many multiplication or addition operations. And so this becomes a very, very large amount of computation that you have to do. And then you have to do this over millions or billions of data records over and over again in order to actually train a model. So this requires a lot of data and computation. And so up until recently, there hasn't been, the performance just wasn't there. So you were only able to build these kind of small or medium neural networks. And basically, when you had, no matter how much data you had, the networks basically wouldn't be able to, perform at the level that they wanted to. That would actually produce something useful. And so only recently have we been able to build these kind of large neural networks that are able to train and on the models actually produce something useful. And we do these using GPUs because GPUs are much faster at the training of machine learning models. And for our image inception model training on ImageNet data, we were able to get 40x speed up with 50 GPUs, and RankBrain, which is our ranking for Google search, was able to get 300x speed up with 500 nodes. So we did it mostly so that you could do this kind of distributed computing. But next I want to talk about TensorFlow itself and how we might actually be able to use it. So what is TensorFlow? So TensorFlow is an open source library it's a general purpose library for doing machine learning. So it was launched last year in November as an open source project. And it's basically our second generation machine learning library. We've previously used a library called Disbelief, but now we're using TensorFlow for all of our machine learning. We basically, once we created this last year, and then we released it as open source almost immediately. So this is the latest and greatest library that Google is using. This isn't something that's really old, and we just open sourced it because we're not using it anymore, and who cares? It's something that we actually are using actively right now. So TensorFlow essentially does the type of operations that I described earlier. It does all of the operating over tensors, which are n-dimensional arrays, but it does this using this kind of flow graph. So TensorFlow, you would write some Python code in order to create this kind of flow graph that is used to train the model, or that is used to build the model. And then that flow graph representation can then be run on a core part of TensorFlow that is written in C++, so it's very, very fast to do the computation. And the internal part of this C++ is able to use map operations to things like CPUs or GPUs. And I'll talk a little bit about that in a second. And we also have these things that we've mentioned also, which are called TPUs. These are custom hardware that Google has been creating to do machine learning within our data centers. So pretty soon, like, people will be able to use these hopefully in the cloud as well. So there's more of those like kind of custom hardware type of things are coming out, and that's really interesting. But like core TensorFlow or TensorFlow itself is has a number of concepts. So TensorFlow itself builds a graph, like I mentioned, and this is basically the computation that's represented as a graph. And then each one of the nodes in the graph is an operation, and then the data that's passed between them is a tensor. So this is very much like the function that I was talking about earlier. But you can build this kind of like, it's like a DAG. You basically can have the output of one operation go to multiple other operations and then combine back again, or things like that. Also part of the programming model are things like constants that you can change between runs. Placeholders. Placeholders are basically the input data to your graph. So this is basically saying like, okay, I'm going to input this type of tensor, which is like X pixel size image of a cat file or a cat image. Variables. Those are the type of things like weights and biases that can be updated as the model is training. So things like the weights and biases you would define as these variables within TensorFlow. And then you have the idea of a session, which is the environment that it encapsulates the environment that you run the graph in. And this is like where you kind of map the graph into or what actually maps the graph into things like the CPUs and GPUs. So here's like a non-exhaustive list of all of the operations that you can do with TensorFlow. There's a lot of built-in kind of operations that you can do that you can do as part of your graph. This is by no means not all of them, but this, as you can see, there's quite a lot of built-in things that you can do as part of your graph operations. So what I want to do here is, my network is not. Let me fix this. So I want to do a demo with TensorFlow here. See if I can pop this up. No. Where did it go? There it went. Let me get my Jupyter up and running here. Oh, come on. So I want to start up this Jupyter. Let's see. Seems to have crashed in the interim. All right. So let me blow this up. So I'm just going to go ahead and restart and clear the output here. But so here's how you would actually use TensorFlow. So TensorFlow, you can basically import as a regular Python module. And so what I'm going to do here is I'm actually just going to run through the MNIST tutorial. And MNIST is a kind of a classic example or test data of doing optical character recognition on numbers. So the MNIST dataset is a dataset of 55,000 28 by 28 pixel images of numbers that are handwritten. So people basically just wrote these handwritten numbers. And what we're going to do is actually use this, or build use TensorFlow to do OCR to detect which number is actually written in these images. And so what each of this is like 55,000 images, but the images are represented as a 784-dimensional array. So that's basically a pixel or a tensor that's 784 dimensions. And each one of the values in each dimension represents a pixel, or the intensity of a pixel. So from 0 to 1, meaning 0 is a white pixel, and 1 meaning a totally black dark pixel. So if I run this here, I can load the data, and then we can kind of look at the image shape. So here's the shape of the image, like as I'm the training data, and here's a sample of what one looks like. So basically, it's a 784-dimensional array, and like most of the pixels are 0, but hopefully somewhere you can see some dark pixels. Like these ones are mostly like pretty much black pixels. So you can see that the dark pixels are set here, and then that kind of represents the image. And then we're going to be feeding this into our neural network. So here's like a visualization of what one of those looks like. So we take that sample image, and then we're just mapping it to plot it on using matplotlib. And you can see that this is an 8. And so that's what we're going to be doing. And then we're going to be outputting as the result of our neural network a tensor that is 10 dimensions, which is essentially just saying that, or it's actually a vector, so it's just one dimension, but it's a hot one vector, which means that it's going to, or it's a vector that's going to give us the probabilities for each number, but the training data is a hot one vector, which means that all of the values in each one of these is 0, except for the one that it actually is. So in the case of the training data, it's kind of shaped in this way, where you have, instead of 780 dimensions, you have just 10 size. And then here's a sample label of one of the training data. So here we can see that this is the sample label for my 8, which says that it's 0. There's basically 0 probability that it's anything except for an 8, and it's 100% probability that it's an 8. So we're going to use this as training data. As the output from the neural network, it'll give you something almost exactly like this, except for it'll give you something that's basically prioritized, or the probabilities that it's each one of these numbers. So the training data itself and the output from the neural network are basically have the same shape, and that's kind of actually important to how we train the neural network. So you saw this picture before. So like once we build this kind of network, we're going to be then using a softmax to make it so that the output of here that's in this tensor, the output tensor is from 0 to 1. And that's basically just done using a softmax. Typically, you find a softmax at the end of a lot of the, right before the output of a neural network. So here's kind of a visualization of what it might look like after you've trained the data. So like based on the probabilities or weights inside of the neural network. So like for a 0, this is a very simple representation of or a very simple neural network. But basically, you can see here that each of these are shown these are showing the weights. So if you see a pixel that's dark in these areas, that's a high probability that it's a 0, or that'll add to the weight or the probability that it's a 0. And if it's inside, there are pixels inside this area, it's going to give a negative evidence or negative probability to the output that it's a 0. And you can see that for all of these, but like because of the probabilities of it being in the pixels being certain dark ones, certain pixels being dark, being attributed to that number, you can kind of see that each of these, the blue areas, kind of look like the number. So you can see here that 3 kind of looks almost like a 3, 8 almost looks like an 8. So you can kind of see that because it's a fairly simple example, but it's kind of a good way of understanding how the neural network is working internally. So here I'm going to actually build the network, and this is actually just this line here. So what we're doing is we're defining a matrix multiplication. So this is actually doing this part of our neural network, which is actually doing matrix multiplication on the input, and then at the end adding the biases. So what we're doing here is doing a matrix multiplication, and then at the end adding the bias, and then we're going to do a softmax on the end of it. So each of these becomes a node in my execution graph. So this matrix multiplication is a node, this adding of the biases is a node, and then the softmax is another node in my graph. And then I'm just outputting. So this is the output kind of tensor operation, and then we can then run this by giving it to the session to tell it to run. So here we've given the variables, as I mentioned earlier. These are going to be updated as I'm training. So the W and B, this is the weight and the bias. And then this placeholder is X. So this is our input image that we're going to be sending to it. So next, we're going to define the train step. So this is actually used for training. So what we're going to use is our gradient descent optimizer. So this is that kind of step that's after actually the model itself to do the training and update the weights and biases. So here what we're going to do is we're going to give it this is called a training. This is the learning. I forget what it's called. It's the learning. I forget it. But it's basically telling it how far to move the gradient optimizer when doing the training. So here this is kind of a visualization of what a gradient descent optimizer is doing. It's essentially saying, okay, I've got this output from my neural network, and then comparing it to the loss function, or using the loss function to determine the cost, like how good was the neural network, and then trying to nudge it in the direction of getting better each time as it iterates through training. So if you make this really, really high, this is going to jump around a lot, and you won't be able to actually find the minimums or which direction to actually go to make your model better. But at the same time, if you make this too small, then it'll take way too long to actually continue to train your model. You'll have to train it many more times. And so you need to find an optimal value for this. Usually about 0.01 or 0.013 is a typical value. And then we're telling it to minimize the cross entropy. This is our loss function. This is what I'm using to say, okay, here's the output from my graph, and how good was the value. And then I'm going to continually check that cross entropy and try to minimize that as I'm going through. So in the example that I showed earlier with all of those layers where I was trying to classify a graph or between the blue and orange pixels, you could see there's a graph in the upper right-hand corner, and as that was going down, that kind of showed the loss over time as I was training. So that's what I'm using to actually do the training. So did I actually run this? No. So now I've created my training step. And then what I'm going to do is I'm just going to do mini batch training, which is basically small batch training over on the data set 1,000 times. And so what mini batch is it's basically just, instead of running over the entire training set, every single time I do an iteration, I'm going to pick a random number of pieces of data from the training set each time, and only train on that. And generally, you get almost the exact same results, but you have to train a lot less data by doing that. So here, I'm going to initialize all the variables, create my session, and then run the init through my session, and then I'm going to actually just create a new batch and run the training step. So this will actually go through and run 1,000 iterations of my training step, and so that's already done. And so then you can afterwards check the accuracy of the neural network by doing by basically training. So here we can do we can run through and check that here we're doing an argmax. So this is actually the output, taking the outputs of my my model and then checking the training data. Or I'm going to do basically a prediction using some of the test data, and then do a prediction on that to see, and then see if the actual value, the correct value, matches the prediction that came out of my neural network. And this argmax is basically saying, like I mentioned, that each of these values that come out of the neural network, each of these is a probability that it's the particular number, the probability that it's 0, probability that it's 1, probability that it's 2, etc. And what argmax is doing is basically just taking the highest value of that and then maximizing that to a 1 and changing everything else to 0. So then we can use that and run an equal, check to see if it's equal, and then do find the mean of all of that. So basically find the average, which will tell us the accuracy of the entire test run. So then we're going to just feed it in the test images and the test labels and tell that to run. And then we can see that that the accuracy that we got out of that was 90%. So that basically might seem good, but that's actually really, really bad. That means that 1 in 10 images is mispredicted or is wrong. So what you would need to do is actually spend a lot more time updating how this updating this to actually do a little bit more of a complicated to build a more complicated neural network in order to make this a lot more accurate. But hopefully that gave you kind of an idea of how TensorFlow works internally and how you might use it for building neural networks. Just as a separate thing, just to give you a comparison, here's what Theano looks like, and doing the same exact training. So Theano is something is a neural network or a library that's very similar to TensorFlow, but it's a little bit slightly more verbose. So what you have here is these are the variables that I was talking about earlier with TensorFlow. You basically have to define these kind of shared memory variables that you use to update as you're training, and then you can build the network pretty similarly to how you do TensorFlow. So here we're doing the dot matrix multiplication. This is a dot product, and then doing adding the biases and doing a softmax. And then, so actually, let's run these. And then we're going to use the same cross-entropy function and define the training step. What's a little bit different from TensorFlow, though, is here you have to do the gradient descent optimization kind of yourself, or if you have to define that update step yourself, which is a little bit annoying, I guess, or a little bit hard to parse. Here is the actual gradient descent, but then we've got to actually do create a function that will do the updating for us to do the actual training. and then we'll build the train model. So this is like my training step in TensorFlow. And then we'll do 1,000 mini batches. If you noticed, I'm actually using the exact same data from TensorFlow. I actually imported from TensorFlow up here at the top. But I'm using the exact same data. And then I just ran that. So then we can test the output. And we can see that we got about the same amount of accuracy out of that, because we're using the exact same algorithm. But the way that you write it is slightly different, but it's very, very similar between TensorFlow and Theano. So kind of going back to the slides here. The real difference between Theano and other libraries is the kind of distributed training that you can do. And so TensorFlow is built so that all of the operations within the graph that you've created can be kind of broken up and then mapped to different devices. So by a device, I mean a CPU or a GPU or so basically a CPU, a GPU, a TPU, any type of like thing that can do computation for you. And then you can map those to actually different GPUs and CPUs on different devices or different machines even in a cluster. And so you could have something like this where you have a kind of a master process that manages things like parameters and worker processes that have the CPUs and GPUs that actually do the computation. So one of the problems with doing distributed computing is because the communication between the machines, and so you have to make the in between the computers as much or as fast as possible using something like RDMA or a fast kind of network. But once you're able to do that, like the TensorFlow is able to make that more theoretically possible in terms of developing applications that do that. So at the end here, I had a little bit about data parallelism. I don't have a whole lot of time to go into this, but this is the type of data parallelism that we use within Google for our training. And there's a couple of modes that you can do for parallelizing the training of models. So one of those is an asynchronous type of data parallelism. So I mentioned that after you've trained the model, you've got to update all the parameters. So as you're kind of looping through this as you're training each of your training batches. And so what this asynchronous version does is it actually will update the parameters asynchronously from each of the workers. But this adds a little bit of noise to your output. Or to your model, because these parameters can only come back into the models asynchronously as well. And so even though device A has updated a parameter, device B might not see it until a little bit later. And so you actually, device B will continue using the old parameter for a little bit. So that adds a little bit of noise, to it, but it makes it a lot more fault tolerant and faster to train the models because it's done asynchronously. But you can also do synchronous data parallelism, and this is a little bit slower, but is a lot makes it a little bit more less noise. So this makes your models a little bit more accurate. So essentially, you have all of the devices do the computation, then update the parameter. And then you wait for all the devices to be finished their operations before updating and then passing the parameters back to the models for the next batch. So this is a little bit more accurate, but it's less. It's a little bit slower and a little bit less fault tolerant because you can lose some of the. You'll lose a lot more because if you lose one of the models, you have to start that whole batch over again. So, and one thing I'll note is up here, this is a little bit of TensorFlow code that allows you to do that. So TensorFlow has a lot of these kind of built-in primitives that allow you to do things like distributed training and asynchronous or synchronous data parallelism. You can also do model parallelism as well, but I don't really have time to go into that too much. Finally, I just want to talk a little bit about where we're going with things like TensorFlow and with machine learning. And so one of the things that Google is going to be is working on right now is to build something called cloud machine learning, which will allow you to build TensorFlow graphs and then run them in a Google data center, essentially, which will allow you to do distributed training with the types of fast networks and fast interconnects. So you can scale your training a lot to a lot more machines than you would normally. And so this is something that's in limited preview right now, but it should be something that most people or most developers can use later this fall to do. And then we'll support regression and classification initially as part of cloud machine learning, but essentially we'll support everything that TensorFlow can do in the future. So basically what it does is it's basically a way to accelerate training with TensorFlow. So normally something that would take 8.3 hours with one node locally would take something like 32 minutes in the cloud. So it's not really, there's not really much to the service from the outside, but you basically just are running the TensorFlow graphs on much faster hardware. So that's essentially the idea behind CloudML and where we're going. But TensorFlow will always be open source, and we hope to see like other environments where TensorFlow is made use of in cloud environments or wherever. So we're really excited about this particular space. And just another plug for the tensor processing units. These are the hardware that we're going to be using at Google that's specifically designed for machine learning. And this gives us a lot better performance per amount of electricity used, which is really, and for those of you that care, it's 8-bit quantization, which is pretty neat. So that's all I had for today. Hopefully that gave you an idea of what TensorFlow is like, and so you can go out and try to get started using it. There's some really good how-tos and tutorials on TensorFlow.org. So if you jump into here, there's like all these tutorials and how-tos. So tutorials is mostly around the machine learning mechanics. So things like how to do Mandelbrot sets, MNISTs, image recognition, things like that. And then how-tos are around like how to put TensorFlow together and run it in a distributed environment, how to put it into production, etc. So you'll want to check out things like distributed TensorFlow, threading in queues, things like that, in order to how to deploy TensorFlow. And then there's a really good workshop that we did at PyCon in the US. And you can get that by going to bit.ly. So go to bit.ly/TensorFlow-workshop. And there's a whole workshop on how to use TensorFlow. And it goes a lot more in depth than my talk. And goes through how to actually run TensorFlow in a distributed manner using Kubernetes and in a Kubernetes cluster. So definitely check that out if you have a chance. So thanks a lot, and I look forward to hearing more about what you guys are doing with TensorFlow. Thanks.
Okay, so I believe we have run out of time. So I believe Ivan will be here. So if you want to have any questions, just come over here, and let's thank Ian again. Okay.
Yeah. So I'll be here I'll be here for after the talk, and so if you have any questions, come down here and grab me. I'll also be around the rest of the day, so if you see me walking around, then just grab me at any time and ask questions. Thanks a lot.